This is a continuation of my previous lecture, which introduced multiple integrals. For the rest of this talk, I want to go ahead and think of the region we're integrating over as just being a rectangle. So the situation looks like this, where again, the function we're integrating is f of xy, and since this dy is in the middle here, this is telling us that y is going from c to d. And when the dy is on the outside, this integral will tell us that y is going from c to d. Here, x is on the outside, x is going from a to b. Here, the x is in the inside, this dx, and so x is going from a to b. What we want to do is find the volume of a solid under some surface z equals f of xy, that's what this is representing, and over a rectangle, where the rectangle is given by these limits of integration for x and y. And the way we're going to do this is by cutting up this solid that we have into thin slices. So in the way of a picture, we want to take a slice where this slice is perpendicular to the x-axis. So this slice here is perpendicular to the x-axis. If I were to continue this, it would intersect the x-axis right here. Now, this x we want to think as being fixed between 1 and 2 inside this slice, and the y for this slice is going to vary from 2 to 4. The thickness of the slice will be delta x, some small change in x. But what we want to do to get the volume of the slice is to take that thickness delta x and multiply by the area of the face. To get the area of the face, we can just read this, but where did this come from? So we imagine to get this area, again, that x is fixed and y is going from 2 to 4, and we want to do a Riemann sum where the rectangles are going up like this. The thickness of a particular rectangle is delta y, and the height is given by the height of our function, which in this case is 40 minus 2xy. So for example, if x were 2, fixed at 2 here, the function z would be 40 minus 4y, and that would be telling us the height at a given y between 2 and 4. So we want to think for a fixed x that the height of our rectangle, and a Riemann sum, is going to be 40 minus 2xy. So when you make that into an integral, you're going to get y going from 2 to 4, and you're going to be integrating the height, the 40 minus 2xy dy. So now we just want to go ahead and integrate this. You can see the 40 becomes a 40y. We're integrating with respect to y. The 2y, when you integrate that, will give you a y squared times the x. So we have 40y minus xy squared. Y is going from 2 to 4. Now I go ahead and plug in 2 and 4. I'm going to 40. For y, I'm going to get 4 minus 2 as y goes from 2 to 4. And then I have a minus x, and y squared as I go from 2 to 4 goes from 4 to 16, so that's going to be 16 minus 4. And so we get 40 times 2, which is 80, minus x times 16 minus 4. 16 minus 4 is 12, so it will be 80 minus 12x. And that agrees with what they have up here, the 80 minus 12x, and that's where that came from. So that's the area of this face for a given value of x between 1 and 3. When we multiply that area by delta x, that will give us the volume of this slice. So this represents the volume of the slice. We're adding up all the slices, and as usual, when we let the delta x get small, the number of slices go to infinity, the sum becomes an integral, where x is going from 1 to 3 again, and a of x stays there, and the delta x becomes a dx. So now we just want to integrate a of x dx from 1 to 3, and we know what a of x is, so we plug that in, and this is what we get. So we get the 80 minus 12x here. We integrate, we get 80x minus 6x squared. Evaluating it from 1 to 3, we'll get 80 times 3 minus 1 for x evaluated from 1 to 3, minus 6 times 9 minus 1 for x squared evaluated from 1 to 3. So that's 80 times 2, which is 160, minus 6 times 8, which is 48. And that gives me 160 minus 48, or 112. So 112 is the volume of this solid. So now, how do we want to think about this? In general, what we really did is we thought of going ahead and taking slices right here, where this was the area of the face. We integrated f of xy, the height, with respect to y. And then we multiplied by the thickness of a slice. And then we summed up over all the slices. The sum becomes an integral, telling us what's happening with x. So delta x became a dx, and x, again, imagine going from a to b, 1 and 3 in this picture. And then this area of the face here is just going to be the integral from c to d, which was 2 to 4 in this picture, f of xy dy. So we get a double integral that represents the volume of this solid. We could have made our slices this way, so it's slightly different now. We have the slices being perpendicular to the y-axis rather than the x-axis. So the thickness now of the slice is going to be delta y, and we want to compute the area of this face differently then, because it's the x that's changing and y we're thinking of as being fixed between 2 and 4. So now, as I take rectangles going straight up here for a Riemann sum, the thickness of those rectangles will be a delta x, and the height will be still the value of the function up here, the z equals 40 minus 2xy at a particular x in this interval, where again we're thinking of y as being fixed. So when we integrate, we're going to have a 40 minus 2xy for our height, and x is what's changing again from 1 to 3. So this will give us the area of this face for a fixed y. So let's go ahead and integrate this. We get 40x. Here the 2x becomes an x squared, so we get minus x squared y. X is going from 1 to 3, so I get 40 times 3 minus 1 as x goes from 1 to 3, minus y times x squared will go from 1 to 9, so this will be 9 minus 1. So we get 40 times 2, or 80, minus 8y. So this is the area of a face. Again, this face here, just like they wrote here. And we're multiplying it by delta y to get the volume of the slice. And then we want to sum up over all those slices, all the volumes of those slices. So this will give us the volume of the solid as we let delta y here go to 0, and the number of slices go to infinity. So the sum becomes an integral. This becomes a of y, and this delta y becomes a dy. Again, we know what a of y is, so we just want to plug in 80 minus 8y for a of y and integrate. So when I do this, I'm going to get 80y minus a 4y squared for that. Again, y is going from 2 to 4, so we get 80 times 4 minus 2 as y goes from 2 to 4. And minus this 4 times, y is going from 2 to 4, so y squared will go from 4 to 16, and we get 16 minus 4 here. So we get 80 times 2, or 160, minus 4 times 12, which is 48. And 160 minus 48, again, is 112. So we get the volume of the solid being 112. Here then, the situation was that we went ahead and found the area of the face by integrating with respect to x. X changed from 1 to 3 here. And then we multiplied that by the thickness of the slice and summed up over all the different slices. And as n goes to infinity and delta y goes to 0, this sum becomes an integral. This becomes a dy. Y is going from 2 to 4 in this solid, wherever it's going from, c to d in general. And here, x is going from a to b in the solid. It's going from 1 to 3. And again, this is just give me this, which is the area of the face. So now we have a double integral, also looking at the problem from this point of view. So these were the two double integrals we got. One, you have dx on the outside here, and one you have dy on the outside. And on the inside you have the opposite, you have a dy and a dx. But we can get rid of the parentheses, and this is how we would write our double integral, either in terms of dy dx or dx dy. These should be the same volume. They're the same solid. I just calculated the volume in a different way. And as you will recall, we got 112 no matter which way we did it. So it's not surprising then we got the same value, but we did get the same value. So let me do an example. This is a solid in the first octant. So being in the first octant means when it's bounded by x equals 2, it's also bounded by 0. So x is between 0 and 2. Y is between 0 and 2 in the first octant. And z is also bounded by 0 from below, but the largest z can be comes from here. Z is going to be bounded by 4 minus x minus y when I take this on the other side. So z equals 4 minus x minus y will give us an upper bound on what z can be. You can see this in a picture. This is the picture of the plane, and the smallest z is going to be is when x and y are both 2, as big as they can be. And when x and y are both 2, z will be 0. That's why it's down here at the bottom here. And then when x and y are both 0, as small as they can be, z will be as large as it can be. And so when these are both 0, z equals 4. So we want the volume of this solid. So we can set up our double integral either way, whether we put the dx dy here or the dy dx. I went ahead and put a dy on the outside. So both these are going from 0 to 2, so that doesn't make too much difference, but the y is going from 0 to 2, so that's what's determining these limits here. This corresponds to taking slices that are perpendicular to the y-axis, and this corresponds to the area of the face of the slice. So I'm going to go ahead and integrate the height, which is the plane here, the z value. The height is z equals 4 minus x minus y again. And that's what I'm going to integrate from 0 to 2 for x dx. So just calculating this, I'm integrating with respect to x, so I get 4x minus x squared over 2 minus yx, again treating the y like a constant. X is going from 0 to 2, so I replace x with 2 and then 0, but 0 you can see I'm just going to get 0. So I'm really just replacing x with 2 here. I get 8 minus 4 over 2, which is 2, minus 2y. So this is 6 minus 2y. Now I now want to integrate with respect to y. The 6 becomes 6y, and then the 2y becomes y squared. So I get 6y minus y squared evaluated from y equals 0 to 2. Plugging in 0 again will just give me 0, so it's only really plugging in 2 here. I get 12 minus 4, which is 8. So the volume of this solid is 8. I should note that there is another way to do this without using calculus, because really, if you just take this solid, turn it upside down and place it on top of itself, you'll just get a box, and the size of the box will be a 2 by 2 by 4 is along the side here. And so it's a 2 by 2 by 4 box, and we want half of that. So the volume can be determined just by doing 1/2 of 2 times 2 times 4, which is 8. But in general, we won't be able to get away with an easy argument like that when we're doing volumes, and knowing how to get volumes by using double integrals or later triple integrals is going to be important in a different lecture. Now, what do you think the point is of this picture? You can see that some of this surface we're looking at goes below the xy plane. So what would that mean? Well, remember when you had an integral in a single variable and the function was below the x-axis, that area that we'd compute wasn't the same thing as the integral. The integral turned out to be negative. It was minus that area. So the same thing happens here. If I have a function which is less than 0, so the z value is less than 0 is negative, and so the surface is going to be below the xy plane, then the value of the double integral here will be negative. It'll be minus the volume that's of the solid between the xy plane and the function z equals f of xy. So you got to keep that in mind as well, just like it was again in a single variable situation, that we don't really just get the volume between the surface and the xy plane unless that function is above the xy plane. Okay, this finishes this